All right, you are welcome again. Okay, today we want to talk about a special topic called Fourier transform. Okay, in previous videos we talked about Laplace, but today let's consider Fourier transform. Now, in this video, we are going to split this into three sections. The first section, we are going to look at the meaning of Fourier transform without mathematical expression or without a mathematical formulas. We are going to see the real life application and meaning of Fourier transform. Maybe you are solving Fourier transform and somebody asks you, what is the meaning of this? What can you see about it? So we are going to explain what Fourier transform is all about without mathematical expressions. And then the second part, we are going to look at Fourier transform and mathematical expressions. Okay? That is explaining Fourier transform using mathematical notations. And then we explain the different terms associated with this Fourier transform. Then lastly, we are going to talk about the basic properties of Fourier transform. Okay, we're going to talk. There are many properties, about 13 of them, but we are going to talk about the most important ones of these properties of Fourier transform. Please stay tuned. Let's go. Now let's start with the first one, which is the basic meaning of Fourier transform. Okay, now imagine you have a special pair of glasses that allows you to see the hidden ingredients of a cake. Okay, now you can see that when you look at the cake, you can see the flour, the sugar, the ingredients, and the other things that made up the cake. All right, let's assume you have a pair of glass that can zoom, that can enable you to see the different ingredients in a cake. You see all those different portions, the sugar, the flour, and all that. All right, good. Now the Fourier transform is just like these special glasses. Okay, now, but you see that this Fourier is for sound or pictures instead of cakes. The same function that these special glasses will help you to see in a cake is what Fourier transform will help you to see in sound and pictures. Okay, now look at this. When you look, or let's say when you listen to music, okay, music is made up of different sounds and different notes. Is that true? Yes. Now, similarly, when you look at picture, picture is made up of different colors and patterns. Okay. Now, the Fourier transform helps us to break down these sounds and pictures into their hidden ingredients, just like the special glasses let you see the ingredients of a cake. All right. Now let's take a look at a very good example. Okay. Now, for example, now let's take a song with different musical instruments. Anywhere in a party, they are playing music or song. You see that in that music, there will be guitar, there will be piano, keyboard, there will be drum, there will be other things, saxophone, a trumpet, and other musical instruments. Okay. Now, when you apply the Fourier transform to that song, what it does is that it separates the sound into different parts representing each instrument. Hello. When you apply Fourier transform to this music, what will happen is that it will separate the sounds, okay, representing each instrument. We can see how much of the sound come from the guitar. We can see how much of the sound come from the drum. You can see how much of the song come from keyboard. You can see how much of the song come from maybe the saxophone, the trumpet, and others. Okay, it's just like taking the music apart and seeing each instrument separately. So that is what Fourier transform does. or that is what it's all about. Now we say that the Fourier transform is a powerful tool that help us to understand and analyze sounds and pictures by breaking them down into their hidden ingredients. It allows us to study and manipulate these sounds and pictures in different ways. Now, you see that this Fourier transform is being used by scientists, musicians, and engineers. Okay, they use this Fourier transform to learn more about the world around us and to create amazing things. Okay, so now you can see what Fourier transform is all about. Okay, the same thing that a special glass does to a cake that helps you to see, to zoom, and able to see the different or the hidden ingredients of a cake is the same thing that Fourier transform will help you to do to sound and pictures. All right, good. Now let's go to the mathematical expression of Fourier transform. Now we say that the Fourier transform is a mathematical technique that decomposes a function of time or space into its frequency components. We see that this is a tool that allows us to analyze the frequency content of a signal or a function. Okay, it is used in many fields, including the engineering, the physics, the mathematics, and signal processing, and what have you. Okay, now the Fourier transform has an equation. Okay, it has a mathematical expression or mathematical notation. Let's see f of omega. Okay, now this f of omega, we are talking about the Fourier transform. Okay, now is given as 1 all over square root of 2 pi, the integral from negative infinity to positive infinity, f of x multiplied by e raised to the power of minus I omega x dx. Okay, and then also we have the inverse to be, we say f of x is equal to 1 all over the square root of 2 pi, the integral from negative infinity to positive infinity, f of omega e raised to the power of I omega x dx. Now please pay attention to these two equations, the Fourier transform and the inverse. You will notice the slight changes. Okay, now in this equation, let's explain these different terms. The first one, the f of omega. This represents the Fourier transform of the function f of x. Okay, now we are talking about Fourier transform operator. So when you perform Fourier transform operator on f of x, what you are going to get is f of omega. Okay, so this f of omega, we call it the Fourier transform. Okay, so it represents the Fourier transform of the function f of x with respect to the angular frequency omega. Okay, now in a simple term, we say that this f of omega tells us how the signal f of x is distributed across different frequencies. When you have taken the function f of x, okay, and then you break them down, okay, now you apply Fourier transform of it breaks it down into the different frequencies of the signals. All right, now let's go. The next one, we have f of x. What is this f of x talking about? This represents the original function or the signal that we want to analyze. This represents the what? The original function or signal that we want to analyze. This could be any kind of waveform or function that varies with time. Okay, good. Now the next one is e raised to the power of minus omega x. Okay, now this term involves the complex exponentials, where I represents the imaginary unit, which is the square root of minus 1. Okay, now we say that this term helps in capturing the frequency content of the signal. The term e raised to the power of minus omega x represents a complex oscillation that rotates at a frequency determined by omega. Hello. Now let's go. What of the omega? Now we said that the omega represents the angular frequency. It is a measure of how quickly the complex exponentials oscillate per unit of time. Okay, now in a simple terms, we say that it represents the frequency at which the signal is oscillating. All right, good. Now let's look at this integral. This integral is a symbol that represents the integral sign. All right, which is a mathematical operation that involves summing up infinitesimally small values. When we say infinitesimal, we are talking about very small or very tiny, okay, values. All right. So over a given range. In this case, it represents the integration of the product of f of x and the e raised to the power of minus omega s with respect to x. Okay, now the dx there is telling us, or we say that it represents an infinitesimally small changes in time. Okay, it is the variable over which we integrate the function f of x multiplied by e raised to the power of I omega x. All right, yes. Now let's go. Now the integral limit being negative infinity to positive infinity indicates that we are summing up the contribution from all possible frequency, okay, covering the entire frequency spectrum. Okay, now let's go. The last one we have here is 1 all over square root of 2 pi. Okay, this is a factor that appears in the equation. It ensures the correct scaling and normalization of the Fourier transform. It ensures that the amplitude of the transformed signals are accurate and consistent. It also ensures that the inverse transform is well defined. Hello. Yes, we call it normalization factor. We call it the nominalization factor. All right. Yes. Now let's go. We have explained Fourier transform using mathematical expressions. All right. Good. Now let's go. The last part, we see the properties of Fourier transform. The properties of Fourier transform. So the first property here we have is called linearity or superposition property. The first property we have here is linearity or superposition property. Now we say that if f of omega and g of omega are the Fourier transform of f of x and g of x respectively, then the Fourier transform of c1 f of x plus c2 g of x is given as c1 f of omega plus c2 g of omega. The same goes with the inverse. Hello. Okay, when you apply the Fourier transform operator on f of x, what comes out is what? The Fourier transform. All right, we say f of omega. Now it has its own symbol. All right, good. So this is the first property. So now, if in our previous videos we have treated the properties of Laplace transform, please, I want you to pay attention or watch that properties. Some of them is very similar here. If you can prove the property, the linearity property of Laplace transform, I'm very sure you can also prove this. All right, good. Now number 2, change of scale. Okay, now we say that if f of omega is the Fourier transform of f of x, then the Fourier transform of f of ax is going to give us 1 all over a f of omega all over a. Hello. So this is called change of scale property. All right. So the proving is also similar to that of Laplace transform. All right, good. Number 3, we have what we call the shifting property. We have the first shifting, we have the second shifting. All right, so now this shifting property says if f of omega is the Fourier transform of f of x, then the Fourier transform of f of x minus a is going to give us e raised to the power of I omega e f of omega. Hello, it's going to give us e raised to the power of I omega e f of omega. All right, yes, this is the shifting property, also the same with the Laplace transform. So number 4, we have what we call modulation property. So again, we say if f of omega is the Fourier transform of f of x, then the Fourier transform of f of x cos x is given as 1/2 f of omega minus a plus f of omega plus a. Hello, so this is called modulation property. Number 5, very important, we have what we call convolution property. Now, what does it state? It states that the Fourier transform of f composition g of x is the square root of 2 pi f of omega multiplied by g of omega. Okay, where f composition g of x is the integral from negative infinity to positive infinity f of x minus y multiplied by g of y dy. All right, yes, this is called convolution property. Then the last one here, number 6, is Parseval's theorem. Parseval's theorem. Okay, now we say that if f of omega is the Fourier transform of f of x, then the integral from negative infinity to positive infinity of the absolute value of f of x, okay, squared dx is the same as the integral from negative infinity to positive infinity, the absolute value of f of omega squared d omega. Okay, yes, this is what this property is talking about. Yes, thank you very much. In this video, we have succeeded in learning 3 things. Number 1, the basic meaning of Fourier transform, the mathematical meaning of Fourier transform, and then the properties of Fourier transform. Yes, thank you very much for watching. Let's take more examples. If you are new to our YouTube channel, do us a favor, subscribe, like, share our videos, and stay blessed.